Hello everyone, my name is Mohamed and I am a first-year PhD student at the Faculty of Science Dar Space at Lizak Laboratory. First of all, I would like to express my gratitude for accepting our proposal paper for this conference. So in this presentation, I will be discussing implementing analog artificial neural networks for enhanced energy efficiency and speed in machine learning applications. This presentation is organized into 4 sections. First, I will start with an introduction. Next, I will discuss the background and the motivation behind this research. Then I will outline the research methodology used. And finally, I will present the results and discuss their applications. So let's start with the introduction. Traditional digital computing methods face challenges like high energy usage and slower speed when dealing with complex machine learning algorithms and large datasets. This has created demand for alternative computing approaches to enable more efficient AI systems. One promising solution is analog artificial neural networks, which use continuous signals processing. Analog circuits are inherently parallel and energy efficient, suiting the operational principles of neural networks. Implementing machine learning models with analog INNs could provide energy efficient, high-speed hardware for AI, overcoming the limitations of digital computing. Next, we have the background and motivation. Analog AI originating from early attempts to replicate human cognition with analog electronic systems like Frank Rosenblatt's perceptron has resurfaced due to the modern need for energy efficient and fast AI applications. Analog computation employing continuous signals provide an alternative to digital computation's binary nature. One of the key challenges in traditional digital computation, including artificial intelligence, is known as the von Neumann bottleneck. The development of AI has resulted in deeper neural networks with a high number of parameters. These parameters are stored in memory and accessed by the CPU, which can lead to slower processing speed. So we can say the von Neumann bottleneck is a major obstacle to the development of artificial neural networks, contributing significant to their slow performance. There is another challenge for the implementation of AI applications known as Moore's law. Moore's law refers to the observation that the number of transistors on integrated circuits double approximately every 2 years. Over time, the size of transistors has approached to atomic scale, leading to significant limitations in hardware design. It is very clear that the software capabilities are progressing in a positive trend, while hardware growth is being limited. As for the motivation behind this work, we can summarize them in 4 main ideas. First, addressing efficiency challenges in AI applications. The need for more efficient AI applications has emerged due to the challenges posed by the von Neumann bottleneck and the slowdown of Moore's law. Exploring analog artificial neural networks, analog computation align well with neural network principles, making it an ideal candidate for implementing machine learning models. Energy efficiency considerations. There is a need for the development of computing paradigms that can achieve a significant reduction in energy consumption while maintaining high performance levels. And finally, contributing to the future of machine learning hardware. This research aims to contribute to the discourse on analog computation by demonstrating the feasibility and benefits of analog INNs through detailed simulations and analysis. We seek to pave the way for their broader adoption in future machine learning hardware solutions. Now we will move to the research methodology. The methodology behind the development, training, and validation of the analog artificial neural network involves several case steps designed to ensure both accuracy in predictions and efficiency in operation. The work is divided into three parts: offline training process, analog implementation, testing, and simulation. Let's start with the offline training process. The backbone of our model's training regimes is a dataset composed of 1,000 entries, each consisting of three input values and their representative numerical outputs. In this work, the analog artificial neural network is built upon a simplified yet efficient architecture that leverages the benefits of analog computation. The architecture comprises three key layers: an input layer, a signal head layer, and an output layer. The network was trained using a digital simulation on a computer by iteratively adjusting the synaptic weights and biases based on a representative dataset of the problem space. Upon completing the training phase, the optimized weights and biases were translated into the analog domain. Programmable resistors were used to implement the weights, while biases were applied using the DC voltage and resistors. To adapt to the electronic domain, certain value translations were made, such as converting negative weights to positive values to accommodate the limitation of resistors. Here we present the analog circuit implementation of our INN architecture realized using LTSpice software. The circuits comprises the three fundamental layers mirroring the architecture of the INN. Each layer of the circuit consists of various components. Neurons are represented by resistors, while the activation function value is implemented using CMOS technology. The sigmoid function is implemented using SPICE code to ensure high precision. Additionally, there are blocks for current to voltage conversion, voltage amplification, buffering, and more. The simulation was conducted using LTSpice software. The three inputs were represented by three DC voltage generators, and the output was a voltage value in the millivolt range. The simulation type employed was transient simulation, which examines the variation of the output over time. Passing to the final section, results and discussion. The errors observed were remarkably low, ranging from 10 to the power of -6 to 10 to the power of -7, indicating a close alignment between the model's outputs and the desired values. This high level of accuracy serves as a testament to the effectiveness of our analog INN implementation. In this table, we compare the results of our simulation with the desired results. At this step, we test many different inputs, and the result always matched our expectations. To conclude, our implementation of analog neural networks is significant first step toward enabling more energy efficient and faster machine learning by utilizing analog hardware's capabilities. The promising initial results encourage further research to optimize analog neural network design and develop specialized analog hardware accelerators, which could lead to major improvements in performance and efficiency when deploying intelligent systems. And thank you for your attention.